In this video we are going to look at some of the important properties of two-dimensional linear transformations. So if we have the transformation given by the matrix ABCD, so it takes the point with coordinates xy through to the point given by ABCD times by xy, then first of all the point 0, 0 will be taken to the point ABCD times 0, 0, which just gives me a times 0 plus b times 0, which is 0, together with c times 0 plus d times 0, which is 0. So we can say that under such a matrix transformation, the image of the origin is always going to be the origin. Now if we consider the point 1, 0, well 1, 0 will go to ABCD times by 1, 0, which gives me a times 1 plus b times 0, which is a as the top element, and c times 1 plus d times 0, which is c for the bottom element. So the image of the point 1, 0 is given by the first column of the matrix. And similarly, if we start with the point 0, 1, then the image of the point 0, 1 will be ABCD times by 0, 1, which gives me a times 0 plus b times 1, which is b as the x-coordinate, and c times 0 plus d times 1, which is d as the y-coordinate. So, under a matrix transformation, the image of the point 0, 1 is always given by the second column of the matrix. Now these two properties are very useful in helping us to determine quickly the matrix for a geometrical transformation, because all we need to do is think about what happens to the point 1, 0, and that gives me the first column of the matrix, and then think about what happens to the point 0, 1, and that gives me the second column of the matrix. So for example, if I want to find the matrix which gives me an enlargement of scale factor 4 and centre the origin, then the point 1, 0 will be mapped by this transformation to the point 4, 0. And that means that the first column of the matrix must be 4, 0. And if we're doing an enlargement of scale factor 4 and centre the origin, then the point 0, 1 is mapped to the point 0, 4. So 0, 4 must be the second column of our matrix. Second example, if we want to have a rotation of 90 degrees anticlockwise about the origin, then a moment or two's thought will tell us first of all that the point 1, 0 maps round to the point 0, 1, which means that the first column of the matrix must be 0, 1. And if we rotate the point 0, 1 by 90 degrees anticlockwise about the origin, then we end up at the point -1, 0. So the second column of the matrix must be -1, 0. Now on the next page there are 3 more examples. And what I'd like you to do is just stop the video at this stage and see whether you can work out what the matrix for each of these 3 transformations is going to be. And the answers are on this sheet here. Okay, so now to push on, if we wish to find the matrix which gives the transformation equivalent to an enlargement of scale factor 2 and centre the origin, followed by a rotation of 90 degrees anti-clockwise about the origin, we can do exactly the same as we've been doing on the previous examples. We'll start off by considering what happens to the point 1, 0, and then consider what happens to the point 0, 1. So the point 1, 0, first of all, when we enlarge it about the centre, with centre the origin, with scale factor 2, then the point 1, 0 becomes the point 2, 0. And then if I rotate the point 2, 0 by 90 degrees anti-clockwise about the origin, that is going to end up being the point 0, 2. If I start with the point 0, 1 instead and do the enlargement, I shall get the point 0, 2. And if I rotate the point 0, 2 by 90 degrees anti-clockwise about the origin, then I will obtain the point -2, 0. So the matrix of the transformation, the first column will be the image of the point 1, 0. So the first column is 0, 2, and the second column is given by the image of the point 0, 1. So the second column is -2, 0. A little bit later on in this video, we'll see an alternative way of answering this question. If we have two transformations, so if we've got a transformation with matrix A, which is then followed by a transformation with matrix B, we want to try and work out what's the matrix for the single transformation with the same effect. In other words, we want the single matrix that will give us the transformation which is equivalent to the transformation with matrix A followed by the transformation with matrix B. So let's track an arbitrary point xy. So if we start with an arbitrary point xy, the image of the point xy after the first transformation is the point x dash y dash, where x dash y dash is obtained by calculating A times xy. The final image of P is going to be the point x double dash y double dash, which is found by calculating B times x dash y dash. But we know that x dash y dash is the same thing as A times xy. So we can say that the final image, x double dash y double dash, is obtained by multiplying B times A times xy. So what we can say is that the matrix BA is the matrix for the single transformation equivalent to a transformation with matrix A followed by a transformation with matrix B. Now it's really important you spot the fact that it appears a little bit odd. BA is the matrix for the single transformation equivalent to a transformation with matrix A followed by a transformation with matrix B. Now we return to an example that we looked at earlier on. We know that the matrix for an enlargement of scale factor 2 and centre the origin is the matrix 2, 0, 0, 2. We also know that the matrix for a rotation of 90 degrees anticlockwise about the origin is the matrix whose first column is 0, 1 and whose second column is -1, 0. So the matrix for the enlargement followed by the rotation is the matrix for the enlargement pre-multiplied by the matrix for the rotation. And if we multiply this across, we've got 0 times 2 plus minus 1 times 0 as the top left-hand entry. So that is 0. We've then got 1 times 2 plus 0 times 0, which gives me 2 for the bottom left entry. For the top right entry, we've got 0 times 0 plus minus 1 times 2, which gives me minus 2. And the bottom right entry is 1 times 0 plus 0 times 2, which is 0. And that's exactly the same answer as we obtained earlier in this video. Two different methods of doing the same thing. We know from our previous video that the rotation of theta anticlockwise about the origin has got a matrix of cos theta sine theta for the first column minus sine theta cos theta for the second column. Replacing theta by phi means that a rotation of phi anticlockwise about the origin has got a matrix cos phi sine phi for the first column minus sine phi cos phi for the second column. And replacing theta by phi plus theta, we know that the matrix for rotation of phi plus theta is going to be cos of phi plus theta sine of phi plus theta for the first column minus sine phi plus theta cos phi plus theta for the second column. But a rotation of phi plus theta anticlockwise about the origin is the same thing as doing a rotation of theta anticlockwise about the origin and following it by a rotation of phi anticlockwise about the origin. So we've got that the matrix for the rotation of phi plus theta anticlockwise about the origin must be the same as the matrix for the rotation of theta anticlockwise about the origin pre-multiplied by the matrix for rotation of phi anticlockwise about the origin. Now if we start doing the multiplication on the right hand side, the top left entry is going to be cos phi cos theta minus sine phi sine theta. And the bottom left hand entry on the right hand side is going to be sine phi cos theta plus cos phi sine theta. Now it's reasonably easy to work out the other two entries in the matrix on the right hand side. In actual fact, for what we need at the moment, I don't want that. So what have we got? Looking at the left hand entries on the left hand side, we've got looking at the top left hand entries, on the left hand side we've got cos phi plus theta, and on the right hand side we've got cos phi cos theta minus sine phi sine theta. So we've got cos phi plus theta must be the same thing as cos phi cos theta minus sine phi sine theta. And looking at the bottom left hand entries on both sides of our equation, we've got sine phi plus theta must be the same thing as sine phi cos theta plus cos phi sine theta. So what we've got now is a really neat proof of using matrices that the compound angle formulae are correct. Now, if we've got a matrix A which moves the point xy to the point x dash y dash, we know that x dash y dash is the result of multiplying A by xy. So if I multiply both sides of that equation by the inverse of A, then we're going to get A inverse times by x dash y dash is the same thing as A inverse times A times xy. In other words, A inverse times A is the identity. So A inverse A times xy is the identity times xy, and the identity times xy is just xy. So, if the matrix A transforms the point P to the point P dash, then if the inverse matrix exists, the inverse matrix will transform P dash back to P. So we can say that the transformation with matrix A inverse undoes the transformation with matrix A. Now, we say that the point P with coordinates UV is an invariant or fixed point of a transformation T if the image of the point P under the transformation T is P itself. In other words, T maps P onto itself. Now, for a transformation T defined by the 2x2 matrix ABCD, we already know that the point 0, 0 always is mapped to itself. So the point 0, 0 will always be a fixed point. The point 0, 0 is always an invariant point if the transformation T is defined by a 2x2 matrix. Are there any other fixed points? Well, it depends on the matrix. So let's see in an example now whether we can find the fixed points of the transformation xy goes to minus 1, 4, minus 2, 5 times by xy. So we're going to suppose that uv is a fixed point. If uv is a fixed point, then that means that minus 1, 4, minus 2, 5 times by uv must give me uv. Now, doing the multiplication, minus 1, 4 times by uv gives me minus u plus 4v. So I've got minus u plus 4v has got to equal u. And the second part of the multiplication is minus 2u plus 5v must equal v. Now, if I tidy up those two equations, I can rewrite those as minus 2u plus 4v equals 0 and minus 2u plus 4v equals 0. And both of those two equations in fact are exactly the same, and both of them just tell me that u must be twice v. So we can say that any point of the form uv where u is twice the value of v is going to be a fixed point of the transformation T. In other words, the fixed points of T form a line with the equation x minus 2y equals 0, or if you like, y equals a half x. Now let's see what this means in terms of a picture of the transformation T. So if we have an object consisting of the triangle UVW, with u being the point 4, 2, v being the point 8, 2, and w being the point 8, 4, then we notice that the point u and w both lie on the line y equals a half x, or if you like, they both lie on the line x minus 2y equals 0. So we're expecting the points on that line to be fixed by the transformation. So when we show the original triangle UVW together with the image triangle U dash V dash W dash, we can see that U dash and W dash are in exactly the same point as U and W. And in fact, all of the points in between U and W have also been fixed by the transformation. Whereas on the other hand, the point V has been moved by the transformation down to the point V dash, which is down at 0, minus 6. Now for a second example, let's try and find the fixed points of the transformation xy goes to 1, 4, minus 2, 5 times by xy. So if uv is a fixed point, then we've got 1, 4, minus 2, 5 times by uv must equal uv. Carry out the matrix multiplication. We've got u plus 4v must equal u, and minus 2u plus 5v must equal v. If we tidy that up, we've got 4v must equal 0, and minus 2u plus 4v must equal 0. 4v equals 0 tells me that v is definitely 0. And then the second equation then just gives me minus 2u plus 0 equals 0. So that tells me u equals 0 as well. So in this case, the only fixed point of t is the point 0, 0. Now our next task is to find a way of finding the image of a line under a matrix transformation. So, as an example, if we wish to find the image of the line y equals 3x minus 2 under the transformation given by the matrix 4, minus 1, 3, 2, what we need to do is we need to start by getting a typical point on the line y equals 3x minus 2. And a typical point could be written as being the point P, 3p minus 2. That clearly is on the line y equals 3x minus 2. Now the image of this point is calculated by working out 4 minus 1, 3, 2, times by p, 3p minus 2. So the top entry is going to be 4 times p plus minus 1 times 3p minus 2. And the bottom entry is going to be 3 times p plus 2 times 3p minus 2. The top entry simplifies to p plus 2, and the bottom. So the image of the line y equals 3x minus 2 under this transformation with this matrix is the line y dash equals 9x dash minus 22. Now we say that a line is invariant or fixed by a transformation t if the image of the line under the transformation is itself the same line. So what we're going to try and do is we're going to try and find the equation of the lines which are invariant under the transformation whose matrix is 8, 2, 1, 7. Entry simplifies to 9p, take away 4. So the image point is x dash y dash, where x dash is p plus 2 and y dash is 9p minus 4. The fact that x dash is p plus 2 tells me that p is the same thing as x dash minus 2, which in turn tells me that y dash is 9 times x dash minus 2, take away 4. In other words, y dash is 9x dash minus 22. So this means that the image of the line y equals 3x minus 2 under the transformation given by the matrix 4 minus 1, 3, 2 is the line y dash equals 9x dash minus 22. Now the final concept that we've got on this video is the idea of an invariant line. And we say that a line is invariant or fixed by a transformation t if the image of the line is exactly the original line. So, as an example, what we're going to try and do is we're going to try and find equations of lines of the form y equals mx, which are invariant under the transformation given by the matrix 8, 2, 1, 7. So, if we have a line whose equation is y equals mx, then a typical point on that line will have coordinates of the form p m times p. The image of this point is calculated by calculating 8217 times by p mp. So we've got x dash must equal 8p plus 2mp, and y dash must equal 1 times p plus 7 times mp. Now, we want the point x dash y dash to also be on the line L. Because if the line y equals mx is an invariant line, then the image point must also be on the line y equals mx. So, in other words, the image coordinates x dash and y dash must satisfy y dash equals m times x dash. So we've got p plus 7mp must equal m times 8p plus 2mp. In other words, we've got p plus 7mp equals 8mp plus 2m squared p. Get everything on one side. We've got 2m squared p plus mp minus p must equal 0. We can divide through by p. We've got 2m squared plus m minus 1 must equal 0, which means that m is either minus 1 or a half. So we can say that the invariant lines passing through the origin for the transformation t have got equation y equals minus x and y equals a half x. Now we can see what this means again by having a look at making use of our GeoGebra representations of the transformations. So in this case we've got an object triangle consisting of U, which is the origin. We've got V, which is the point 4, 2, and that lies on the line y equals a half x. And we've got W, which is the point minus 2, 2, which lies on the line y equals minus x. So what we're expecting to see is that the line UV is invariant under the transformation, and also the line UW is invariant under the transformation. So when we see what the transformation does to triangle UVW, we obtain this large purple triangle. Now you can see what's happened here, that point U dash is still the same as the point U, it's the origin, but the line UV has now become the line U dash V dash. It's the same line as the line UV, but the point V has moved to the point V dash. Now the point V was the point 42, the point V dash is the point 36, 18. So the point V has moved to a point V dash which is 9 times further out from the origin than V was from the origin. The line UV, that's the line y equals a half x, is an invariant line of the transformation, and points along that line have moved out along the line by a factor of 9. Looking at the point, the line UW, U is fixed by the transformation. The point W, which was the point 2, 2, sorry, it was the point minus 2, 2, has moved to the point minus 12, 12. The image point is still on the line y equals minus x. So the line y equals minus x is invariant under the transformation, but W dash is 6 times the distance from the origin that W was from the origin. So the transformation has the effect of sending points on the line y equals minus x out by a stretch factor of 6. So we can mark in our 2 invariant lines for the transformation, and we can comment that the transformation gives us a stretch of factor 6 along the line y equals minus x, and a stretch of factor 9 along the line y equals a half x. To conclude this video, there's an exercise here which covers several of the different concepts that we've looked at in this unit, in this video. And it'd be a good idea if you've got time to have a go at these 3 questions.